Yes, so now in today's session, we are starting with measures of association. So when I say association, we are talking about two variables. Association is between two variables. So measures of association consist of covariance and correlation concept. As the name suggests, covariance and correlation. Again, co means two. So relationship between two variables and the variance between two variables. So we'll start with measures of association now. And now if you can look at these graphs also. We have discussed this kind of graphs in scatter plots, and that scatter plot is actually the base concept of this correlation and covariance. So we'll be using scatter plots at multiple times now. Even in case of regression, we have to first draw the scatter plot and then only we can go for the trend line. I guess we have seen how to draw the trend line in one of the examples. So similar kind of things now we are going to do in measures of association. So look at this example. Now this example consists of a table of two variables, temperature in degree centigrade and ice cream sale value in dollars. Now what you can understand from these numbers? Any guess?
Like as the temperature increases, the ice cream sales also increases.
Correct. Very good. Very good. So if I try to draw a scatter diagram for this, I'll get similar to something like this. And from the scatter diagram, I can say the overall trend is upward. So as X increases, Y also increases. That means as temperature increases, my ice cream sale is also increasing. And that this kind of relationship is called as positive relationship. This is a positive relationship between X and Y, between temperature and ice cream sales. So we can easily see that warmer weather leads to more sales of ice cream. Temperature and ice cream sales are related to each other and it is positive relationship. Simple. Now we'll look at another example. Sunglasses versus ice cream sale. So on x-axis, we are plotting the sale of sunglasses, and on y-axis, we are plotting the sale values of ice creams. Even in this case, I'm not giving the actual data to you, but from the scatter diagram, again, we can see the overall trend is upwards. That means there is a positive relationship. That means, can I say now that if sale of sunglasses increases, also the ice cream sale will increase? Can I say that? Does this mean that sunglasses make people want ice cream, more and more ice cream? Actually, answer is no. Actually, answer is no. So just because of the two set of numbers I have, one set of number which is having the heading ice cream sales and second set of number which is having the heading sunglasses sell, I cannot just create a relationship between these two variables. There is no logical relationship between these two variables. Now there can be an external factor. There can be an external factor which is creating this kind of relationship between ice cream sales and sunglasses sales. That is weather. For example, that third factor or external factor is weather, warmer weather. Because of which people are also going and buying the sunglasses and people are also going and buying the ice creams. But as such, between these two variables, there is no direct impact. Not for any reason that because I'm going and purchasing a new sunglass, I'll also go and purchase the ice cream. No. So as such, there is no direct relationship between these two variables, but because of some external factor, both the variables are showing me positive relationship. And that is very important to understand in statistical analysis or data analytics, that correlation and causation are different. The concept of correlation and the concept of causation is different. Correlation is only based on numbers, pure numbers, nothing to do with logic. Causation is with relationship with logic. So a correlation does not mean that one thing caused the other change in the other variable. So there could be other reasons, external factors, that the data has a good correlation. So correlation is different and causation is different. So in statistical analysis, what we generally focus on at this level is to find the correlation between two variables. That doesn't mean that we are going to prove the causation also. So we cannot use statistical analysis to prove the causation also. Okay, fine. Now we'll go to the next example. Now look at this example. We are plotting height of the employees on x-axis and we are plotting number of leaves taken by these employees on the y-axis. Now if I plot the height of the employees and number of leaves, and if I look at the graph, there is as such no relationship. It's very scattered format. So we cannot find any general trend as upward or downward or something like that. So it's scattered. So we can say that there is no relationship or zero relationship. So height and number of leaves are not related to each other, and it is a zero relationship. Now, as we have discussed in last few sessions that in this course, as part of this course, we are going to discuss only linear relationships. So when I say linear relationship, what I mean by that is the relationship which can be presented by a straight line. It can be a positive, negative, or any kind of relationship, but a relationship which can be presented using a straight line. That is a linear relationship. So suppose you, in some case, if you find a relationship something like this, for example, if I try to draw a relationship, these are my data points, suppose. So now for these data points, can I try to fit all the data points using a straight line? No. What I have to do is I have to draw a curve, exponential curve. So this becomes non-linear relationship. This is not a linear relationship. Or in some cases, I may get a relationship something like this. If I try to plot data points and if I'm getting a relationship something like of a U curve, this is not a linear relationship. So linear relationship means when I try to fit all the data points using a straight line, either upwards or downwards. So in this course, we are going to discuss all the linear relationships and even the regression models based on the linear relationships. Measures of association. In statistics, dependence refers to any statistical relationship between two random variables or two set of data. Correlation refers to any broad class of statistical relationship involving dependence. For example, this is what we have discussed: correlation between demand and product and its price. So both are, I can say, they are in positive relationship. Correlation between electricity demand and weather, yes, they are dependent on each other. In above examples, there is a causal relationship also, but that is not the focus of the statistical analysis. There may be causal relationship, but that we cannot prove using statistical analysis. So statistical calculations of correlation is to find dependency where usual relationship may or may not be present. So causal relationship is present or not present, that we cannot find out using statistical calculations. So there are several correlation coefficients often denoted as rho or R. So as you can see now, rho is a Greek character, so it is for population, and R is for sample. Measuring the degree of correlation. The commonest of these is Pearson correlation coefficient, which is sensitive only to linear relationship between two variables. So all these things are kind of theory part. So we'll just finish all this theory part quickly so that we can shift on Excel. Other correlation coefficients have been developed to be more robust than the Pearson correlation, and which are more sensitive to non-linear relationships also. Now, if you just look at this graph, this diagram, what can you understand from this diagram? What is your observation from this diagram? Actually, answer is given to you, but I want you to explain this. Why correlation and causation are different, and how you can say this based on this example.
Like I'm not sure, as the temperature increases, the cells of umbrellas are also decreasing.
No, your observation is not that correct. Actually, the half part of the image shows if it is raining, the people will carry the umbrella. In case of rainy season, people will carry umbrella. So if an observer is looking at the situation, what observer thinks is there is a relationship between umbrella and rain. So now, is it a one-way relationship or two-way relationship? Because it is raining, people are taking umbrella. But is it true that if I go out in the sunny day and if I take the umbrella, it should rain? No. That means causal relationship.
No.
Okay, so that's why the meaning is correlation and causation are different. Okay, so now I'll go ahead now. Now you can look at different graphs. Now the first graph shows a negative relationship. You can see a downward trend. So this graph shows a negative relationship. And the value of R. Now R, we have discussed that R is used to denote the coefficient of correlation. So R value is negative because negative relationship is there. So R value is negative, but the value is 0.9. Fine. Now, when I say R is 0.9, what is the meaning of that? Now, in case of relationship, again, we are going to discuss the concept of deviation. So, if my data points, are very close to the trend line, if my data points are very close to the trend line, that means the deviation of my data points from the mean line or expected line is very less. Then that means my value of R is going to be very strong. It may be 0.9 or 0.85, something like that. But now, if I compare that this example with another example where I have again upward trend, positive relationship, but my data points are not that close to the trend line. There is a deviation of my data. There is a considerable deviation in my data points from the trend line. Automatically, you will see the value of R is 0. Maybe 6 or 0.5. And if they are very much dispersed from my expected line, like these are my data points, but they are showing me the positive trend, then the R value is 0.2 or 0.1. So from the R value, I can say if the R value is close to 0.1, if the R value is close to 0.1 on both the sides, negative or positive, if R value is close to 0.1, the deviation of my data points from the trend line will be very less. And you can see the last example where R value is exactly 1, and you can see the trend line. My every data point is falling on the trend line itself. My every data point is falling on the trend line itself. So my deviation from my trend line is 0, almost 0, very close to 0. So you will get different types of relationship graphs, and based on that you will get different types of R values, and this is a relationship between R value and the graph. So this is a downward relationship, negative relationship, so value of R is negative. And if I try to draw a trend line, all my data points will be very close to my trend line, and that's why the value of R is 0.9. We are going to see how to calculate the value of R. Now look at second example. Again, this is, we have a negative relationship. So if I try to draw a trend line, I will get a negative value and I can draw a trend line, but the deviation of my data points from the trend line will be more compared to the first graph, and that's why the value of R is 0.5. And look at third graph. All the data points are in dispersed format, scattered format. There is no relationship. That's why the value of R is 0. R is 0.50, similar to minus 0.50. This is positive relationship. So similar, if I try to draw a trend line, the deviation will be there from my data points with the trend line. This is positive relationship, and if I try to draw a trend line, all my data points are very close to the trend line, so the value of R is strong, that is 0.90. And this is what we have discussed. If I draw a trend line, all my data points are exactly falling on the trend line, that's why the value of R is 1. So based on the values of R, we can define the type of relationship. And this is the scale of that. The value of R is always between -1 to +1. So if it is between -1 to -0.75, we say it is a strong negative relationship. Then between -0.75 to -0.25, we say it is a moderate or intermediate negative relationship. Moderate is a proper word. -0.25 to 0 is a weak relationship. 0 itself is a no relationship. Similarly, on positive side, we can have weak, moderate, and strong positive relationships. So based on value of R, now you can properly define what type of positive or negative relationship you have between two variables. Now, how to calculate R? So now we have discussed what is correlation, why we need correlation, because we want to differentiate from the causation in itself, and then we want to predict the future values or the values which we don't have with us. Now, how to calculate correlation, how to calculate R? So this is the value, this is the formula for covariance, first of all. So first we need to find out the covariance. So what is the variance between two variables? And then we can use this covariance to calculate the correlation. Now, why the formula of covariance is like this? Now, what is the concept of variance? We have discussed the concept of variance. When I say variance, variance is xi minus x bar, that is the mean, bracket square, square deviation. Variance is square deviation. Now, because we have only one variable, in case of variance, we have taken xi minus x bar bracket square. But now what we are looking at is covariance, that is variance between two variables. Variance between two variables. So if I'm talking about variance between two variables, what I will do is I will say xi minus x bar and yi minus y bar. The distance or the deviation of my data points for x from the x bar and for y from the y bar. So instead of taking square, taking same distance twice, what I'll do is I'll multiply the deviations of between x and between y, and then I'll take the summation. Now, as per the definition of variance, we have to divide it by n, but that is for sample, that is for population. In case of sample, you may have seen this concept multiple times in statistics, in multiple reference books and textbooks, that whenever we deal with sample, generally we consider n minus 1 instead of n. And if we are dealing with population, we consider n. Now, this concept is called as, I'll just tell you what is this concept is. This is called as degree of freedom. This concept is called as degree of freedom, that in case of sample, we always take n minus 1, and in case of population, we take normal n. That concept is called as degree of freedom, and it is not that every time we take n minus 1. In case of sample, if you are calculating a statistic, you have to less 1 degree of freedom per statistic. So if it is confusing you, you can just leave this part. Others who are interested in statistics only, pure statistics, they can try to find meaning of this statement, that if you are trying to calculate one statistic, then you have to have 1 degree less of freedom per statistic. Fine. So in case if I'm in some formula, for example, if I have mean also and standard deviation also, that means I'm using two statistics. I'm using two different statistics in one formula. Then I have to less 1 degree of freedom per statistic. So I have to use n minus 2. Fine. But now, right now, what we'll discuss is why we are using n minus 1. What is the meaning of degree of freedom? Any guess? Anyone? Why? What is the meaning of degree of freedom? Anyone?
Maximum minus minimum.
Okay. Anyone else?
Rows or
okay. So I'll just explain you the meaning of degree of freedom with one example. We will not go into more details, that is not required. But what is degree of freedom conceptually? Suppose if I want to do addition of three numbers. If I want to do addition of three numbers, and I want that addition to be 10 or anything, suppose 10. It can be 0, it can be negative, anything. My situation is I want to add three numbers resulting into 10. So do you have complete freedom to select first number? Do you have complete freedom to select first number? Yes. I have complete freedom to select first number. It can be anything. It can be 1, it can be 1 lakh, it can be minus 223, it can be 0.5, it can be a fractional value, negative value, positive value, it can be anything. There is no restriction on me to select my first number. Suppose I select my first number as minus 223. Considering my first number as minus 223, do I have complete freedom to select my second number? Again, answer is yes. I have complete freedom to select my second number also. Even if my first number is minus 223, again I can select any number as my second number. It can be again 1 lakh, 0.89, it can be anything, any fractional value. Suppose I select 8.9 as my second number. Now, considering my first number is minus 223 and my second number as 8.9, do I have any freedom to select my third number, considering my addition has to be 10? Now the answer is no. Now the answer is no, that I don't have any freedom to select my third number, because if the addition has to be 10, then I cannot select any number as my third number. That is a restriction for me. Then how much less degree of freedom I have? Out of 3, I have 2 degrees of freedom. Out of 3 numbers, I have 2 degrees of freedom, that is n minus 1 degree of freedom. So whenever we talk about sample, because we select few from the population, as we go on selecting one by one all the sample points, we don't have any freedom to select my last sample point, and that's why we consider that degree of freedom as n minus 1. So for every sample calculation, the degree of freedom is always n minus 1. Fine. So that is all about degree of freedom, and this is the explanation of the covariance formula. Why covariance formula is like this. So if you calculate this covariance value, that is denoted by Sxy, because that is a covariance between x and y. S stands for standard deviation, and between x and y, so Sxy. And that becomes my numerator for correlation calculation. That becomes numerator, Sxy, divided by Sx into xy, individual standard deviations. So standard deviation of x and standard deviation of y. That is a simple formula for correlation, covariance between x and y, divided by standard deviation of x multiplied by standard deviation of y. But we are not going to use this formula, and we are not going to calculate correlation and covariance using pen and paper. We are now directly going to use the Excel and the tools in Excel to calculate correlation, covariance, and based on that we'll do some analysis. Okay, so we are going to solve these two problems. So this is what I am getting as scatter diagram. Now what we have to do is we have to find the relationship, or we have to analyze this scatter diagram for the relationship between two variables. So from this scatter diagram, I can say there is a downward relationship. There is a downward relationship, so that shows negative relationship. So when I say negative relationship, the value of R will be negative. Okay, fine. So I'll just mention here somewhere that it is a negative relationship. Oh, it is by default considering because of minus sign, negative relationship. And in second case, I can see the common trend as upward trend. Upward trend. That means there is a positive relationship between x and y. So I'll just write that it is a positive relationship. So we have a negative relationship in first example, and we have positive relationship in second example. Now if I try to draw a trend line, add trend line, if you click on any data point and if you right click, you will get option add trend line. Now you can see that I'll not display any equation or something right now. This is my trend line for first example, and if I try to draw a trend line for the second example, now this is what I get as a trend line for the second example. Now look at both the examples. From the example itself, I can try to visualize my value of R. In first example, out of 5 data points, my 3 data points are exactly on the line. My 3 data points are exactly on the line, and the data points which are not on the line are also very close to my trend line. So the value of R will be, because it is negative, I can say value of R will be very close to minus 1.0. The value of R will be very close to minus 1.0. So it must be somewhere around minus 0.9 to minus 1.0 range, correct? In second example, if I draw a trend line, out of 5 data points, only 1 data point is falling on the trend line, and the remaining data points are having considerable distance from my trend line. It's not that I can say that the data points are close to my trend line. No, there is a considerable distance from my trend line. So I can say that this can be a kind of moderate relationship, and because it is positive, I can predict my value should be somewhere between 0.4 and say 0.7, somewhere around 0.4 to 0.7. Now I'll try to find the relationship value also using Excel. So how to do that? For that, we have a formula called as correlation. C-O-R-R-E-L, correlation. So just type equal to and type the formula name, correlation, and you can see the description. It returns the correlation coefficient between two data sets. Simple. So into bracket, what I have to do is I have to give both the data sets as input. So first, I'll give the first data set, which is values of y, comma, I'll give second data set, which are the values of y, values of x and values of y. And if I hit enter, what I'm getting is the R value. This is the R value, relationship value, relationship coefficient, Pearson correlation coefficient. So minus 0.96, and that is fitting our assumption that because of the trend line, my value should be between -1 and -0.9. Yes, it is -0.96. So I can say this is a strong negative relationship between X and Y. There is a strong negative relationship between X and Y. And in case of second problem, if I use the same formula, equal to correlation into bracket, first data set, comma, second data set. So what I'm getting is 0.69. So yes, it is positive, but it is not strong positive. It is moderate positive. It is between 0.4, 0.7. Yes, our prediction was correct, that it is between 0.4 to 0.7 because there is a considerable distance between my data points and the trend line. So it is 0.69. So even by without calculating R, just by looking at the trend line and the position of data points, how they differ from the trend line, you can try to understand the relationship coefficient also. And directly you can calculate correlation coefficient using the formula correlation. Now this is first method. This is first method to calculate correlation. There is another method to calculate correlation in Excel. What you can do is you can go to data tab, go to data analysis option. In data analysis option, you will find one method called as correlation, one tool called as correlation. Just click on correlation tool. It will ask for input range. So input range means the data from both the variables. So I'll say X and Y. I'll select complete table, X and Y, all values with label. Because I'm having label in my first row, I'll just click on label in first row option. Yes. So while calculating correlation, this tick means don't consider the values in the first row because they are labels. It is text. Group by column. Yes, my data is group by column. Output. Suppose I want to start my output from this location and just click on OK. So what it gives me is the same value of R, what we have calculated, -0.96. But that will get displayed in a matrix format. So relationship between X and X is 1, has to be 1. The relationship of X with Y is -0.9688. That is what we have got. Again, relationship between Y and Y is also 1. Why it is not displaying the value between Y and X? Because it has to be same. If the relationship between X and Y is -0.96, the same value will get repeated here. Now these are called as symmetric matrix. These kind of matrices are called as symmetric matrix. So in that case, even if you don't display this value, that is understood that the same value is getting displayed here. Now when we have a direct function, correlation to calculate relationship between two variables, why we need this option? Why this option is there in data analysis with correlation 2? The reason for this is, I'll just copy this problem and I'll paste it here. And suppose I have another variable Z. Suppose I have another variable Z, and now I want to find a relationship between three variables. So I'll take some values for Z. Suppose I copy the values of Y from the next problem. Okay. So in this problem, now I want to find correlation between X and Y, correlation between Y and Z, and also the correlation between X and Z. So one way to do that is to use correlation on multiple variables. Like first I want to find between X and Y. So I'll provide the arguments as values of X and values of Y. Then to find correlation between Y and Z, I'll give values of Y and values of Z as arguments. And then third time I have to use the correlation function to find the correlation between X and Z. So I'll provide the values of X and values of Z. So this is between X and Y. This is between X and Z. Y and Z. And this is between X and Z. Now it is okay because we have three variables. We can do this. Suppose if we have 5 to 6 variables, 10 variables, then instead of repeating this process multiple times, now this method is more feasible and more beneficial to go for correlation, because this allows us to select all the variables at a time. This allows us to select all the variables at a time. So I'll just select X, Y, Z, all the variables, all the values, including labels. and suppose then now I want to start my output from this location, and I'll click on OK. So it is giving me the same values, minus 0.96 for between X and Y, then 0.33 between Y and Z, and minus 0.12 is between X and Z. It is giving me the same values, but on single click, I can get all the relationship values. That is the benefit of this data analysis method. So you can find out the relationship between multiple variables using a single click. And again, as I have explained, that these three values, we don't have to show values in these three cells, because it is understood that if the value relationship value between X and Y is minus 0.96, the same will get reflected here. The X and Z value will get reflected here, and Y and Z value will get reflected here. So these are called as symmetric matrix, and what we are displaying is called as the lower part of symmetric matrix. Okay, so that is how you can calculate correlation coefficients in Excel. So these are the two methods, either using formula or using the data analysis method. Fine. So from the R value also you can see, and from the trend line also you can see that the deviation of my data points from the trend line is very less. So they are very close to the trend line. That means there is a strong negative relationship. There is a strong relationship basically. Now, what is the use of this trend line? From this trend line, I can say that the values which are not present with me. First is the values which are not present with me. I can try to calculate those values. So I don't know what is the value of X is equal to 10. So I can try to predict value of X is equal to 10. Roughly, the value of X equal to 10 is going for value of Y is equal to somewhere around 68, 67. So for value of X is equal to 10, I can expect value of Y as 68 or 67, somewhere around. Now, when I say 68 or 67, that is based on the scatter diagram which I have. Now that is the expected value. When I say value of X is equal to 10, Y becomes 67. That becomes my expected value of Y for X is equal to 10. Now when I say expected value of Y is 67 for X is equal to 10, my actual value, if I actually take X is equal to 10 and suppose if I go ahead and if I get some value of Y, the actual value of Y may be different from 67, and that deviation will be something in numbers. But based on the value of R, what I can understand is that deviation will be small. If I'm expecting value as 67, if I'm expecting value of Y as 67 for X is equal to 10, because there is a strong relationship, minus 0.97, very strong relationship, I can expect that my actual value will max deviate between 65 to 68. That deviation will not miss. I'll not go wrong with the deviation because of the strong relationship. I can say the deviation will be between 65 to 68. So my range of deviation is very less based on the behavior of other data points. And that is what we understand from the strong relationship, moderate relationship, and weak relationship. In case of weak relationship, if this number could have been 0.37 or something, I cannot be so much confident or so much sure that my range cannot go below 65 and cannot go above 68. No, it can be anything, because I cannot predict how much deviation will be there. But because there is a strong relationship based on the behavior of other data points, I can say if my expected value is 67, I can expect maximum deviation of between 65 to 68. Okay, so that is what you can understand from the R value. Now consider if I add another data point in this table instead of 10 as 7 and suppose 90. If I add a last data point, that is my new addition, which is not part of the original data. So if I'm adding a data point into this table with values 7 and 90. Now we'll try to see how the addition of one data point is going to affect my value of R, or is going to change the value of R. Okay, so maybe instead of 90, I'll take value as 100, better for understanding. Okay, so now again we'll try to draw the scatter diagram with the new values. I'll go to insert and then scatter diagram. Now this is my new scatter diagram. If I try to add the trend line, this is the trend line. and then I don't want all these values on the x-axis. So I'll click on format and I'll go for 40, the same value. Now all other points are like same, but now this data point, I have added a new data point, which is this data point. Now, is it going to change my R value? So I'll just minimize this so that I can display the R value here itself. Okay, so I'll use the formula for correlation, and then I'll supply both the data sets with the addition of the last data point. Now look at R value. Now R is getting decreased from 0.97 on negative side, it is coming to 0.89, almost 10% of decrease. So the relationship quotient is decreasing by almost 10% just by addition of one data point. So that much of shift is happening in terms of quotient of relationship. And that's why in such cases we can say that this is a probable contender for the outlier, being outlier, this data point. This data point probability is more that this data point will turn out to be an outlier. And this is another method to find out the outliers from the scatter diagram and from the trend line. In further slides, I am going to explain you how to do analysis based on residuals in scatter diagram. So we have discussed the concept of correlation and covariance, and now we have seen how to calculate correlation in Excel and how to interpret the value of R and what all you can understand from the correlation value. Now the next concept in case of measures of association and the concept which is based on the relationship between two variables is regression, concept of regression. So the definition and the meaning of regression is very important, and I'll explain more details about regression with the help of example also. So first we'll look at what is line of regression. Actually the trend line which we have drawn in Excel, that trend line is nothing but the linear regression line. So from day one, whatever trend line we have drawn, actually we have done regression only, but we have not used that regression line for analysis. So today we are going to look at the analysis part of that regression line. So we'll start with the presentation now. Regression indicates the degree to which the variation in one variable x is related to or can be explained by the variation in another variable y. That is a definition of regression. Now what is the meaning of this line? Now when I say there is a relationship between x and y, when I say there is a relationship between x and y, what is the meaning of this statement? There is a relationship between x and y. For every value of x, I can try to predict value of y. For every value of x, I can try to predict some value of y. There is a relationship between x and y. It can be positive or it can be negative, but there is a relationship between x and y. So this also indicates that if I change something in x, if I change something in x, it is also going to change something in y. It is also going to change something in y. If I change x, x is going to change, y is also going to change. That is the meaning of relationship, correlation. So if I change something in x, that is going to result in some change in y also. So when I change something in x, and if it is changing something in y also, how much of change in y, how much of change in y can be explained by x? How much of change in y can be explained by x? And that is nothing but analysis of regression. So if you look at the definition again, regression indicates the degree to which quantification we are trying to do quantification, the degree to which the variation in one variable, the variation in x, the change in x is related to or can be explained by, the variation in another variable y. That is the meaning of regression, that how much of change in one variable can be explained by change in another variable. How much of change in y can be explained by change in x. So that is the concept of regression. In this case, if the change in y can be clearly explained by x, if the change in y can be clearly explained by X, I can say that X is a good predictor of Y. X is a good predictor of Y. So X can predict Y more accurately. X is a good predictor of Y. And to understand or to know whether my X is a good predictor of Y or not, we have to do this regression analysis. So that is the definition, and that is the meaning, and that is the reason why we are doing regression analysis. Once you know there is a significant linear correlation, you can write an equation describing the relationship between X and Y variables, because that is a significant linear relationship, that linear correlation, that means it is a straight line, and we know the equation of straight line. Equation of straight line is y equal to mx plus b, where m is the slope of the line and b is the y-intercept. So in case of regression, we need to know, or we need to calculate the value of m and the value of b, because x will be given to you. X will be given to you. So if you know m and b, you can easily predict value of y. So how to calculate this m and b? So the formula for calculation of m and b is, this is the formula for m and this is the formula for b. Now we are not going to use pen and paper to calculate m and b, and that is not required in Excel also. We have some direct methods to calculate all these things. So if you calculate m and b using this formula, and if you put that m and b in this equation, that becomes my regression line equation. That becomes my regression line equation. Now you can notice while writing regression line equation, we are not writing plain y, we are writing y cap. Y cap is equal to mx plus b. Why we are writing y cap is because if I just write y equal to mx plus b, this is my expected y. When I put value of m, value of b, and some value for x, and if I calculate, what I get is the expected value of y. Expected value of y, that is not the actual value of y. If I just write y, that indicates actual value of y. So to differentiate between actual y and expected y, we put a cap sign. So y cap indicates expected value of y. So we can calculate expected value of y using y equal to mx plus b, which is a equation of straight line. Now we will use this formula, we will use these calculations, and I'll show you one example also. Suppose I have a data set with two variables, x and y. We have some values for x and some values for y. We have 7 different values, where x is number of absentees by a student and y is the final grade. So x represents how many times a student is present in the class or not present in the class, absentees, and y is the final grade received by that specific student. So student number 1 was not present for 8 sessions, and student's final grade is 78. Student number 2 was not present for 2 sessions, and the final grade is 92, and so on. So this is what I have data about number of absentees and the final grade. So I have to calculate, or I have to represent this data using equation of regression line. So for that, first I have to calculate m, and then I have to calculate b. So I'll just calculate m and b using this formula. So I'll show you how to calculate. You have to calculate xy product, x square, y square, and all these things. Just substitute all these things, and what you get is minus 3.924, which is the value of m, and 105.667, which is the value of b. Now if this is the value of m and this is the value of b, which I have received from the calculations, then I can write the line of regression as y cap is equal to minus 3.924x into plus 105.667. So that becomes my equation of regression line. So this m is a coefficient of x. This m is a coefficient of x, and y is the b is the y-intercept, which is a constant. B is the y-intercept. So this is how you can calculate using pen and paper, but we are not going to use pen and paper. We are directly going to use Excel for all these calculations. So now the next method to calculate the regression line equation, go to data analysis, and in data analysis you will find one method, one tool called as regression. You will find one tool called as regression. Just click on OK. It is asking for input y range and input x range. So give y values in y range and x values in x range. So these are my y values. So I'll select all the y values including label, and input X range. So these are my X values including the label. Yes, I'll tick on labels. My first row consists of labels. Confidence level. Now this we will discuss in tomorrow or day after tomorrow's session. So by default it is 95%. So keep it 95%. Output range. Suppose I want to start my output from this location. And from all the things, what I want is only residuals. Because we are now going to do some residual analysis. So I just want to display the residuals, the deviation of my data points from the trend line. And I'll click on OK. If I click on OK, you will get something like this, some output, something like this. So you look at this output. What is the R square value? 0.95, which is the same which is getting displayed on the chart. Now the value of M, which is the coefficient of X, and the value of B, which is a constant. You will get the same values in this table. The intercept value, the B is what? B is y-intercept, the constant. The intercept value is 105.668. And the X coefficient, so X coefficient is minus 3.924, which is the M value. So even from this option, you can come to know the regression line equation. If these values are like this, you can directly write the equation as y is equal to minus 3.924x plus 105.668 easily. So now we are going to discuss about all these things in today's session itself. And in tomorrow and day after tomorrow session, you will come to know about all these things. You will come to know about the ANOVA table. You will come to know about T statistics. You will come to know about P values. You will come to know about these ranges and everything. These are called as intervals, 95% interval. So all these things we are going to discuss in next two sessions. So this is another way to calculate intercept and X coefficient. Now what is the meaning of R square? The important part is R square. What is the meaning of R square? And before that, okay, just look at the residual output. The residual output, if you look at the headings of residual output, it will give the value of residuals considering the predicted Y. So what is the observation number 1? The value of observation number 1. So I'll just copy the Y values. So observation number 1 is 78, which is the actual observation. The predicted Y as per the equation, regression line equation, the predicted Y is 74.27. So what is the deviation of my actual value from the predicted value is 3.72. That is my residual for first observation. Likewise, I am trying to find out residuals for all the observations. And from residual, what kind of analysis I can do is I can try to find the extreme data points. From residual analysis, I can try to find the extreme data points. So from this residual analysis, I can say that this is the point which is having maximum residual. This data point, second observation is having maximum residual or maximum deviation. So maybe this can be outlier. Right now we cannot say that much strongly. For that we need to first do R square analysis. But in next problem we are going to do some analysis based on residuals also. And this is how to read the residuals. Fine. So now we'll come back to the R square. What is R square and what is the meaning of R square? Now in this case R square is 0.95. In this case R square is 0.95. So I'll tell you one statement to know what is the meaning of R square. My statement is the change in Y or the change in Y can be explained by X at 95%. Or I can say 95% of change in Y, almost 95% of change in Y can be explained by X. Almost 95% change in Y can be explained by X. That means if I'm changing something in Y, if I'm changing the value of Y by 100, for example, I can predict that change using X at 95% level. That means my X is a good predictor of Y. That means my X is a good predictor of Y. If the change can be explained at 95% level, my X is a good predictor of Y. That means number of absentees and the grade which the student will get in the final score. If I want to predict value of Y based on X, that prediction will be at 95%. That prediction will be correct or accurate up to 95%. My X is a good predictor of Y. So that is explained by R square. Higher the R square, better is the confidence in my value of Y or the change in Y. So when I say R square is 0.95, that means 95% of the change in Y can be explained by X. That means X is a good predictor of Y. Now, what is the meaning of adjusted R square and everything that we'll see in latter part of the session. But now, as you have understood R square, now we'll try to calculate more R square values and we'll try to analyze more data sets. So we'll go to the next sheet. In next sheet, we have a data set of education against earnings. So what is the basic qualification, basic education of a person, and what kind of earnings that person is getting? And maybe it is in thousands. So the education is up to 8th level and earning is 77,000. The education is up to 10th level and earnings is 77,000 again. The education is up to 14th level and the earning is 2,73,000, something like that. So I have a data set with two columns, education details and earning details. So I'll consider education as X and earning as Y. So based on now this data set, now we'll try to draw first the scatter diagram. We'll try to understand the relationship between two variables. Then we'll draw the trend line. We'll come to know the regression line equation. We'll calculate the R square. We'll calculate the residuals and we'll try to do analysis based on all these values. So the first thing is to calculate correlation. So I'll use the direct formula correlation and I'll give all the values of X as the first argument and values of Y as the second argument. Okay. So the relationship value, R value is 0.4. Now this tells me, first thing, there is a positive relationship. And second thing, it is a moderate positive relationship. So it's not a strong relationship, there is a moderate positive relationship. So when I say moderate positive, that means education and earnings are not tightly coupled. That doesn't, this means that if I have higher education, that doesn't mean I'm going to get a higher salary. Probability is there, but that chances are very less. The relationship, at least this data shows the relationship is moderate in nature, 0.4 only. Okay, fine. Now we are going to draw the scatter diagram also. So we'll select all the data points and then I'll go to insert scatter diagram. Okay, so this is what I am getting. Scatter diagram is this. Even from scatter diagram, now we don't have any values on x-axis till 5, so I'll remove that portion. I'll go to format axis and then minimum is, I'll keep it as 5. Okay. From scatter diagram also you can say that there is not a good relationship between these two variables. The spread is more into data points. Fine. So now I'll select data points. I'll try to draw the trend line. Add trend line. I'll display the equation on chart and the R square value both. So this is my equation of line and the R square value equation. Okay. Now you look at the data points. My trend line is here. My trend line is here and my data points are at a long distance from the trend line. So the deviation of my actual data points from the expected data points is more, and that's why R is very moderate, 0.4 only. And look at the R square now. Because there is a weak relationship, moderate or weak relationship between X and Y, and the spread is also too much, the value of R square is also very less, 0.17. What does that mean? That means the only 17, up to only 17% of change in Y, up to only 17% of change in Y can be explained by X, can be explained by X. So this also tells me that X is not a good predictor of Y. This X is not a good predictor of Y. So only education is not a good predictor of earnings. Only education as a factor is not a good predictor of earnings. That is what I can come to know from this graph. Now I'll go for regression also. So I'll go to data, data analysis, regression, and now it is asking me for input Y range. So I'll select all the Y values and then input X range. So I'll select all the X values, including label. So I'll keep a tick on labels. Confidence level, I'll keep it at 95%. Output, suppose I want to start my output from this location. And yes, I want to display residuals also. So this is what I'm getting. I'm getting the same R square, 0.17, the same coefficients, minus 240 is the constant, 57.93 is the X coefficient. And now if you look at the residual output, these are my residual outputs. These are the deviations from my predicted value, expected value. Now we are going to do some residual analysis also. I'll just keep the graph here itself so that I can use the graph for residual analysis also. Okay. Now in this case, if you try to understand the deviations, look at all the deviations and try to tell me the highest deviation, 682. This data point seems to have the highest deviation. Data point number 15. Then the next highest deviations are like 530. This is another data point having highest deviation on the positive side. Anything in the range of 500, yes, this is the third one. So I have these three observations in the range of 500 or above 500 on the positive side. Do we have anything on the negative side which is 500 or greater than 500? Yes, we have this data point which is greater than 500 and nothing more. Okay, so we have these four data points which are actually telling me that they are having highest deviation from the expected data points or expected values. So maybe these four data points are my outliers. So whatever analysis I am doing in my data set, if I try to remove these four data points from my data set, and if I rerun the regression, and if I get a better result or the result which I can accept, then I can say surely that these four are my outliers. But even if after removing these four data points, if I'm going to get a similar kind of R square or maybe a slightly modified R square, but still which cannot be accepted, then I can say these are not the outliers. Whatever my assumption is that X is not good predictor of Y is correct. Only education cannot accurately predict the earnings for any person. So what your task is now, in next 2 minutes, just remove observation number 7, 15, 16 and 25 from your data set and rerun all these things. Again calculate R, again draw the scatter diagram, again run the regression, again run the residual output, and then give me the overall analysis of the new data set after removing these 4 points.
Values are getting relationship is not getting stronger. We are getting weaker relationship now.
Yes. So this indicates that there is no problem with our data. There are no outliers in my data. The problem is between the understanding of variables. I am trying to link education with earnings, but earnings, the education is not a good predictor of earnings. So I should not try to predict about earnings only based on education. So there can be some other factors which I have to consider in addition to education. Only education cannot accurately predict earnings. And that is also true in real life also, that you will see more multiple cases where a less educated person is also getting good amount of money and a very highly educated person is also getting very less amount of money. So only education is not a good predictor of earnings. You need to have some other factors apart from education to predict the earnings. So this is all about whatever we have done till this point is between 1y and 1x. We have only 1y and 1x. In analysis, we call this y variable as a dependent variable. In analysis, in statistics, we call this y variable as a dependent variable because we are trying to predict earnings using education. So earnings are dependent on education and we are trying to check that claim basically. So y is my dependent variable and x becomes my independent variable. So education is a normal variable, independent variable. If I change education, I am expecting some change in my earning also. If I change my education level, I'm expecting some change in my earnings also. That means if I change X, that is going to reflect some change in Y. So Y is dependent on X. So Y becomes dependent variable and X is independent variable. So whatever analysis we have done till today, till this problem, is considering one dependent variable and one independent variable. And in case of one dependent and one independent variable, there is not much to explain about adjusted R square considering R square value. Adjusted R square value comes in the picture when we are dealing with multiple independent variables. And that is the case of multiple regression. When we have one dependent and one independent variable, that is single regression or normal regression. But when we have one dependent and multiple independent variables, then it becomes multiple regression. And that is what we are going to do in the next problem. If you go to next sheet, you will find one dependent variable Y, which is infant mortality, and you will find multiple independent variables. In this case, we have three independent variables, X1, X2, and X3. X1 is the percent adult literacy, X2 is the percent primary school level, and X3 is the GNP per capita. Now, I am trying to predict Y. I am trying to predict Y with the help of these three variables, X1, X2, and X3. So now that means we are doing multiple regression. We are doing multiple regression. So first thing, we'll follow the same process now. First thing, we'll try to find the relationship between Y and X1, then Y and X2, and then Y and X3. Just to know how my independent variables are related to Y. Okay. So first I'll find the correlation. So I'll go for correlation between Y and X1. So this is between Y and X1. Then I'll go for Y and X2, then Y and X3. Only three relationships I want to find. And that's why I'm going for individual method, not for the data analysis method. So comma X2. And then correlation between Y and X3. So these are my correlation values. And from correlation value, I can say basically first thing is all my independent variables are negatively correlated with Y. The relationship is negative. In that case, X1 is having, I can say, moderate negative relationship. X2 is also having moderate relationship, maybe a strong negative relationship because 0.75 onwards is strong. So both X1 and X2 are on the edge of moderate and strong negative relationship. X3, if I consider value of X3, it is very weak negative relationship. So considering individual variables X1, X2, and X3, if I go for relationships, they are having negative relationship, and out of which X1 and X2 are having strong negative and X3 is having weak negative. But that is individual relationship between X1 and Y, or X2 and Y, and X3 and Y. If I combine three variables and then if I try to find the relationship of effective relationship of the combination of three variables with Y, then the picture may be different. And that is what we are now going to analyze, that whether the three variables, combination of these three variables, are a good predictor of Y or not. Now I am going to check whether the combination of these three variables is a good predictor of Y or not. Fine. Now the next step is actually scatter diagram, but that we cannot draw with multiple variables. So we'll directly go to regression. So I'll go to data tab, go to data analysis. In data analysis, go for regression, click on OK. Input range of Y. So this is my Y. So I'll select Y with label. And input X range. Now in case of input X range, I have to select all the independent variables in one shot, including label. I have to select all the independent variables with values and including labels. There are three independent variables. I'll select all three columns with values, with labels. Labels, yes, I have my labels in my first row. Output, suppose I want to start my output from this location. Yes, residuals. I'll still go ahead with residuals for this problem at least, and I'll try to do residual analysis also. And then I'll click on OK. What I'm getting is this output. What I'm getting is this output. Now from this output, look at the R square value. The R square value tells me about how strong my data model is. The R square value tells me about how strong my data model is. So what is my data model? In this case, my data model, if I have to write the data model, it is, I can say my data model equation is y is equal to y, which is the infant mortality rate. That is my dependent variable. So y is equal to, in case of multiple regression, it becomes m1x1 plus m2x2 plus m3x3 plus b, which is the constant. Now because we have three independent variables, we have m1x1, m2x2 and m3x3 plus b, and you can find all those values here in the coefficient table. In coefficient table, the intercept is 154, which is the value of b. Then the coefficient for percentage adult literacy, which is my x1. So this is my m1 value, 0.677, negative 0.677. That is my m1 value. My m2 value is the coefficient of x2, which is 0.59, percentage finishing primary school. And GNP per capita is minus 0.002, which is my m3. So if I have to write the equation, I can write the equation like y is equal to the value of m1, which is minus 0.067 into x1 plus the value of m2, that is so it is minus 0.59 x2 minus 0.002 x3 plus the constant is 154.20 something. So now this becomes my regression equation, or I can call this as my data model. This is my data model to predict y. This is my data model to predict y based on three independent variables with this equation. So this R square is trying to tell me how good my data model is. How good my data model is, that how accurately I can predict y using these three independent variables. So R square is 84.59. 0.8459. That means I can say up to 84% of variation in y. Up to 84% of variation in y can be explained by these three x values. Can be explained by these three x values, which is a good value. Considering R square as 0.84, which is a good value. So if I'm trying to predict y, and if I can predict y up to 84% of accuracy, that means this is a good data model. Or I can say this x1, x2 and x3 as a combination are good predictors of y. As a combination are good predictors of y. This is what I can come to know. Now we'll look at the residual output also. If you look at the residual output, all the data points are having very good or rather very small residuals, except this one data point, which is having highest residual, which is 20. The deviation is highest in case of data point number 9. So I'll just copy the countries just to know the data points labels. Okay. So Zimbabwe. So highest deviation in terms of residuals is for the country Zimbabwe. That also indicates that whatever is my data model, which I think based on R square value is a good model. That means my x1, x2, x3 are good predictors of y. Even if this data model is good, and even if the x1, x2, x3 are good predictors of y, the same data model, the same x1, x2, x3 may fail to predict accurate y for Zimbabwe, because I guess, or I think, because of the highest deviation, highest residual, Zimbabwe may be the outlier. Zimbabwe may be the outlier. So how to check that whether I'm correct or not? What I'll do is I'll just remove Zimbabwe from my original data. I'll remove this line and I'll rerun the regression for remaining table, and I'll see what is the change in R square. If R square is changing on the positive side, and if that change is significant, That means Zimbabwe is outlier. So can you do this thing in next 2 minutes? Just remove Zimbabwe line and rerun the regression for remaining table.
So 0.90.
Very good, 0.90. And what is the adjusted R square?
Is 0.86.
0.86. Excellent. So now I will tell you the meaning of adjusted R square. Now with by removing Zimbabwe, I am getting a better R square. That also indicates me that my analysis was correct, that Zimbabwe is an outlier. If I remove this Zimbabwe from my data set, I'll get a better model or more strong model. This also indicates, because I'm not changing my model. My model is, I'm keeping my model fixed, x1, x2, x3 to predict y. I'm just removing one of the data entry from my data set. That also indicates that whatever is the data model I'm trying to build, that data model is very good. That data model is very good for all the countries except Zimbabwe. So maybe for Zimbabwe, I have to consider few different variables, or maybe I have to exclude some of the existing variables. So I don't know whether I have to add another x4 for Zimbabwe so that it will be a good model for Zimbabwe only, or I have to exclude x3 also. I have to just consider x1 and x2. So I'm not sure about that, whether I have to add a new variable or whether I have to exclude the existing variable for Zimbabwe. And that is given by adjusted R square. Adjusted R square tells you about whether all the independent variables which are part of my data model are a good fit for the model or not. All the independent variables which are part of my data model are a good fit for my data model or not. And how to read the adjusted R square value. Now look at the previous values. The previous values are 0.84 and the adjusted R square value is 0.78. If you look at the difference is 0.06. The difference is 0.06. And in the new values, the difference is 0.04. The difference is 0.04. So even the difference between R square and adjusted R square is getting reduced in without Zimbabwe data set. So the more close the adjusted R square is to R square, if the difference is very less, that means we have taken good and correct independent variables in my data model. If my adjusted R square is close enough to R square, that indicates there is no need to add any new variables, or there is no need to exclude any existing variables from my data model. In case if I get adjusted R square as 0.58, for example, just for understanding, if R square is 0.84 and if my adjusted R square comes as 0.58, that means the difference is huge. The difference between R square and adjusted R square is huge. Though my R square is 0.84, which is a very good value of R square, because adjusted R square is 0.58, that tells me that I can increase this R square. I can increase this R square if I add some variables, or if I can remove some existing variables. So I need to change my independent variables. What is the final conclusion? The difference between R square and adjusted R square tells me whether I need to have some changes in my independent variables, whether to add or remove any variables from the independent variable set. And now based on that, even in this analysis, you can see if I remove Zimbabwe, I am getting better results in terms of R square and adjusted R square. So my data model is very strong. If the difference is 0.04, that is almost negligible. My data model is very strong, and x1, x2, x3 are very good predictors of y, except Zimbabwe, where I think I need to consider few more variables to predict infant mortality. That is the final conclusion of the analysis based on R square, adjusted R square, and residuals.